In this lesson, I want to show you how to use the UART port of your microcontroller so that you can communicate with your PC. So we're going to write a program that when you type R, the red LED turns on. If you type G, the green LED turns on. And if you type blue, the blue LED turns on. And if you type any other character, then the LEDs turn off. Notice that I don't have any circuit connected to the board. We will be using the built-in serial port that's in your board. So you don't need any extra components for this lesson. What you will need is a serial communication software. The one that I'm using is called PuTTY. Let me go ahead and show you where to get it. So if you go to this website, and I will be posting the link in the description of the video, you want to click on this link and download the software. Let me show you how to configure the software. So go ahead and download the program and open it. Let me close the current session that I'm running. And I'm going to go ahead and open the program. Click run. So this is where you configure your serial communication software. And we need to configure it so that it has the same settings as our board. So to get the settings from the board, you want to go to My Computer, right click, Manage, go to Device Manager. Make sure that your Stellaris or Tiva C series board is connected. You should be able to see this drop down menu called Ports. Right click on your virtual serial port. Also note that the address of the port is COM4. Go to Properties. These are the port settings that we will have to configure our serial software to, as well as the code that we will be writing. So write down these settings in a sheet of paper or anywhere you like. So in this window, click on the serial option, change the serial line to COM4 so that it matches your Stellaris board. The speed is 9600, which is what I have in this window also. And you don't have to worry about configuring the data bits in parity or the stop bits, since those are the default for PuTTY as well. But you can go to serial if you want, and actually let me change the flow of control to none as well. So once you have done that, go ahead and click open. So that should open your serial port window. But go ahead and close it for now, and let's go ahead and check out the circuit on the board. And you will be reopening that program once we have programmed the software that we write into the board. So let's check out the circuit that the board uses to communicate with the PC. So if you look at your board, it actually has two microcontrollers. One is used for debugging. This is the one where you actually upload the software to. And this is the USB port that we're using to communicate to the PC. And there's actually a connection between this chip and this chip. So this chip sends the data to this one, and then this one sends it through the USB port. Notice that this is U1, this is U2. So if we go to U1, you'll see that at pin A0 and pin A1, we have a UART connection. So we have the two pins that are used for UART, RX and TX. Notice that one that they say U0, that's UART 0. And it says UART 0 because your microcontroller actually has more than one UART module. So if we go to the datasheet of your microcontroller to section 14 for UARTs, you will see that we actually have 8 UARTs. So the UART that is connected between the chip U1 and U2 is UART 0. And then this chip translates the UART into a serial communication that the PC recognizes. There are actually other options. You don't have to use another microcontroller to communicate to the PC. You could, for example, build an RS-232 shield like the one that the Arduino has. The problem with this type of shield or circuit is that notice that this port is a serial port and your computer may not have that type of port, so you would need some type of converter like the RS-232 to USB converter. So if you use this type of circuit, you're gonna need this type of cable, but there's actually a better alternative. There's a company called FTDI that makes chips that translate from UART directly to a USB serial communication. So they have a driver that gets installed in your computer, and on one side you connect your UART pins. As you can see here, you have RX and TX, as well as your power pins, and on the other side you have your USB connection. So this is the circuit that you would need if you wanted to build something like this. And the Tiva C series board and Stellaris board use 3.3 volt logic, so if you buy something like this, make sure that it is 3.3 volts. But like I said, you don't need any extra components for this lesson, since we will be using the connections that I showed you in the datasheet. Alternatively, and this is actually a better alternatively, and I also wanted to show you that this type of connection is one that the Arduino 2009 used to use. So if you check out their schematic, you will see the same schematic here for the FTDI chip. So notice how the let's go ahead and find the pins. That's TX and RX, and they go to M8RX, which goes to PD0 and PD1 of the microcontroller. So this is the Arduino microcontroller, this is the FTDI chip, that's this one here. New versions of the Arduino use a similar setup like the one that the Stellaris board uses, which is 2 microcontrollers. My favorite way, however, is to use this type of cable. So this cable is built by the same company that makes these ICs, and the cool thing about this cable is that all of this circuitry is built into the cable. So you can find this cable in Mouser. Just make sure that this is the name of the cable. It was actually meant to be used for the Raspberry Pi, but it also works with your Stellaris board. So you have three pins. One is ground. This is your transmitting cable. This is your receiving cable or pin. So you can find that in the datasheet for this cable. So you would use this cable if you didn't want to use the UART 0. Let's say, for example, that you wanted to use UART 5 instead of UART 0. So if we go to UART 5, so UART 5 would be pin 4, PE4, and PE6. So these are the 2 pins that you would have to connect to this FTDI cable. So now that you have seen the hardware that the Stellaris or Tiva series board use to communicate to a PC, and now that you know about other alternatives, let's go ahead and talk a little bit about the UART protocol. So I'm going to use this Wikipedia page, and so the UART protocol consists of a start bit followed by 5 to 8 data bits and then a stop bit. You also have the option of having a parity bit, which tells you if the data is even or odd, in case you need that type of information. We won't be using parity, and we will be sending 8 data bits or 1 byte. So our signal will consist of a start bit followed by 8 data bits and 1 stop bit. A UART connection between two devices consists of 3 lines. One is the ground line that is common to both devices. The other 2 lines are the receiving line and the transmitting line. The transmitting line from one of the devices goes connected to the receiving line of the other device and vice versa. So in this Google search that I did for UART communication, it looks like they are communicating a GPS device with a microcontroller. And I will probably show you how to do that in another tutorial. I actually have a UART GPS device. If you connected the TX or RX pins to an oscilloscope, this is what you would see. So this is the signal that I told you we were sending. This is your start bit, your data bits. Can be either 1 or 0, and your parity bit is optional. So now that you know how the UART communication looks like on hardware and on a signal, let's get started with the code. So like in my previous videos for the SPI interface and the I2C interface, I have used the steps provided by the datasheet of your microcontroller, which are located in section 14.4, and they end right before 14.5. So I have copied the steps in this datasheet and pasted them in my C file. First thing we need to do is we need to enable the UART module that we're using. We're using UART 0, so I have to set the bit for UART 0 in this register. So if you go to this register, you will see that you have 8 UART modules available. UART 0 is located at bit 0, and we have to set it to enable it. Since UART 0 uses port A, as I have shown you in the datasheet, this is PA0, PA1, and that is UART 0. So UART 0 uses port A. That means that we have to enable GPIO for port A. So that is a bit for port A. Port B would be bit 1. Port C would be bit 2, for example. Next, we need to enable the alternate functions on pin PA0 and PA1. So that's PA0, this is PA1, enabling the alternate functions on this register. We don't have to worry about the current level or the slew rate for this tutorial. Once we have enabled the alternate functions, we need to select the specific alternate function using the PMCN bits. So if we go to the configuration section for UART, and we are in step 5, and then we go to this table, you will see that UART 0 is located at column 1. So that means we have to put the value of 1 in the PMCN bits. So we go to the GPIO PCTL register, which contains the PMCN bits. This PMC0 represents PA0. So we have to put the value of 1 from the table in these 4 bits. In PMC1, we also have to put the value of 1 since PMC1 represents PA1. So PA0 starts at bit 0 of this register. PA1 starts at 4. So this is enabling UART 0 on PA0, enabling UART 0 on PA1. And since they are digital signals, then we have to enable the digital functions for the pins. So that's PA0, this is PA1 for the digital enable register. Now that we have configured the UART pins for input and output, or rather enable the functions, we have to configure the UART module. So what we're gonna have to do is we're gonna have to calculate some baud rate divisors. The baud rate is the rate of transmission, how many bits per second the microcontroller will send. If you recall from the device manager window, we are going to be sending 9,600 bits per second. So that is our baud rate. And you can actually find this equation in the datasheet. So these are the settings that they have in the datasheet, but we are using 9600 instead. We are using 8 bits. So this is the formula. The formula that they give you assumes a clock of 20,000 or 20 megahertz. The clock that we're using is the default clock, which is 16 megahertz. So go ahead and plug in 16 megahertz in here. Go ahead and plug in 9,600 in this number, and this will be the value that you get. So what we need to do is we need, for the divisor, we need the integer, and we also need a divisor fraction. The divisor fraction is calculated using this formula. So you take what's left of your decimal, you put it here, rest of the numbers stay the same, and this integer function means that you truncate the number that you get. So you do not round up or down, you simply, for whatever answer you get from this equation, you take what's left of the decimal. And that formula is also in the datasheet. So just make sure you have those numbers, because we will be putting them in some of the registers for the UART0 module. So the first thing that we need to do is we need to disable the UART module by clearing this bit. This bit is located in bit 0 of the CTL register. So if you go to your register descriptions and you go to UART-CTL, you will see that at bit 0 you have the UART enabled bit, and we want to disable it, so we have to clear the bit or make it 0, and that is what I have done in this line. Next thing we do is we need to write this number in this register and this number in this register. So that is our baud rate divisor that the microcontroller uses to send the right amount of bits per second. Our desired parameters, once again, if you check the device manager window properties, these were our parameters: 8 bits, no parity, 1 stop bit, flow control none. So you configure those in this register, and the default is actually no parity and 1 stop bit, so we don't have to worry about those bits. But if we go to bit 5 of this register, you will see that that's where the word length is set. So the word length is how many bits we're sending per transmission. We're sending 8, so I have to put the value of 3 starting at bit 5 of the LCRH register. So that's the value of 3 at bit 5 in this register. Next, we have to select the source for the UART clock. This register gives us several options. So that is the UART clock configuration register. And the options that we have is to use the system clock or PIOSC. The default system clock is actually PIOSC, which is 16 megahertz. So I'm gonna go ahead and use the system clock, and that was actually part of our formula. We won't be using micro DMA in this tutorial. Once we have configure the UART module, we have to re-enable it. Remember that in this step we had disabled it, so we have to enable it now. Let's go to the CTL register to see what bits 8 and 9 are. So this is the UART control register. So bit 0 enables the UART when it's set. Bit 8 enables the transmission, and bit 9 enables reception. And note that it says here that in order, you can't just enable one, you can't just enable the transmission without enabling bit 0, as it says in this note. So that is why in order to enable the UART, you have to set these 3 bits and not just bit 0, which is the UART end bit. Like I showed you in the beginning of this video, we are going to be controlling the LEDs, so we also have to configure the LED pins. So I'm enabling port F, making the directions of the pins outputs, enabling the digital functions of the pins. I showed you in one of the first videos of this series that the LEDs were in port F. So all of this is nothing new if you watch that video. And then we turn off the LEDs. So our UART is configured, the LEDs are configured. Let's go ahead and send some data to the computer as well as read some data from it. So I've actually made a function called print string and another one called read character. And don't forget to declare those functions at the top of the file. So my print character function is the one that sends a character or 8 bits through the serial connection between my microcontroller and my computer. First thing you need to do is you need to make sure that any previous transmission has ended. So we go to this register of the UART module. So that is my UART flag register. Notice that in my code I'm checking bit 5. So this tells you the state of the transmission. When its value changes to 0, that means that we are done transmitting any previous data. The data register is not full. That means that, or rather the transmitter is not full. So that means we can fill it up with some data. And that is what I do in my next line of code. So this is my data register. It's an 8-bit register if I'm not mistaken. So that's the UART data register. This is where you put the data in these 8 bits. So you simply load up the data and the transmission begins. And before you load it again, of course, you have to check to make sure that it's done transmitting. So that is what this function does. My read character, on the other hand, checks for bit 4 on the FR register. So my flag register F4, while it's 0, that means that my receiver is not empty. So I'm checking until it won't be equal to 0. So when the receiver is not empty, it means it has some data in it. When it's 1, it means that the receiver is empty. So by me putting this while loop in here, I am stopping the program and waiting for the user to put something into the UART module data register. So this waits until the user puts something in the types something on the keyboard. Once the user types something on the keyboard, then bit 4 in this register changes to 0, and once it has changed to 0, then I can go ahead and read the data that the user typed and save it into a byte variable. Remember that a character is 8 bits of data. So to print something, I write to the data register. To read something, I read from the data register. But before I read, I have to make sure that there's something in it to read. And before I write, I have to make sure that everything that needed to be written was written. Additionally, I've actually created another function called print string. So if we wanted to, for example, send a sentence using print character, use this function once for every character. With this function, I created a pointer and I check until my pointer is null, and while it's not null, then I send the data byte by byte. So in this case, I send the ENTER. This is my new line character. This is my carriage return character, so that the words that you see on the screen don't just keep moving to the left. So the /R returns the text or aligns it to the left of the screen. So what I'm doing here when I increment the pointer is I'm incrementing the address where the pointer is pointing to. So initially I load this string into this variable, and of course every string has a null character at the end, which is actually /0. So that is what I'm checking for in here. And then I change the pointer, and when the pointer is pointing to /0, then I get out of the while loop and I don't print any more characters. So this is where I prompt the user to enter the letters R, G, or B. I then wait until the user types something in the keyboard, and then I save that data in this variable, which is a character. I then print whatever the user typed. So if the user types something and I don't print it back to the user, he or she won't be able to see what they are typing, so I have to print the character back. I also want to make sure once again that I create a new line and a carriage return for the user's character. Lastly, I have a switch statement for the character that I received. If it's an R, then I turn on the red LED. If it's a B, then I turn on the blue LED. If it's a G, I turn on the green LED. If it's any other character, then I turn off all the LEDs. So now that you have written your code, go ahead and compile it. Upload it to your board. Press go. Minimize this window. Go ahead and open PuTTY. Choose serial, COM4. Or whatever other COM you have in your device manager. The number might be different for yours, so change the number accordingly. The speed that we have programmed in the microcontroller. Press open. Well, before that, make sure that you have 8 data bits, 1 stop bit, no flow control, no parity. Press open. Go ahead and type R, G, or B, and then any other character to make sure that your code is working as expected. That's it for this video. Thank you for watching.